It's got to be one of the oldest, deepest questions we've ever tackled in science.
It really has. And for ages, centuries even, going way back.
Right, from ancient thinkers all the way up to Newton.
Exactly. The idea was gravity's this invisible force, something reaching out across empty space, pulling things together. Mysterious.
But then, early 20th century, Einstein just turns it all on its head.
Completely. A total revolution in thinking. He said, look, it's not a force in the traditional sense.
It's geometry, the shape of space-time.
Precisely. The curvature of this four-dimensional fabric, space-time as he called it.
Yep.
That's general relativity. And, well, it's been incredibly successful over a century now.
Okay, yeah. And yet, that gut feeling, that intuitive idea of something more mechanical, it sticks around, doesn't it?
It does. It's tempting to think simpler sometimes.
Like maybe that whole curved space-time thing, I don't know, just a complicated way of describing something else.
Yeah.
What if gravity is more like a drag effect?
You mean like friction?
Yeah, maybe caused by matter itself. The idea being you get close to something big, like a planet, you run into thicker stuff somehow, and that pushes you, redirects you into an orbit. It sounds kind of simple, maybe even elegant.
Well, that's exactly the kind of hypothesis we want to unpack today. Really dig into it.
Okay.
Our aim here isn't just to wave it away. We want to engage with the idea seriously, test it against what we actually observe, against the core principles of physics we know work.
Right. So let's chart this out. First, we need to really get a handle on the modern view, Einstein's geometric picture. Why physicists think it's, basically necessary given the facts.
Makes sense. Lay the foundation.
Then we can dive into this drag effect idea. Where did it come from historically? And crucially, why doesn't it actually work? Why is it fundamentally untenable?
And we should probably clarify that whole thing about planets being round, too, how that fits in.
Good point. And explore the really solid empirical proof we have that space-time curvature isn't just math, it's like real.
Absolutely. The observations are key.
And finally, maybe put this all in context. Look at the frontiers. What do legitimate challenges or alternatives to Einstein's theory look like today?
Yeah, because science is always pushing boundaries.
Yeah.
But, and this is the core message, I think, while looking for intuitive models is, part of scientific history.
Sure.
This specific drag effect idea, it runs smack into huge problems. Things like energy conservation, a really fundamental principle. It's also been shot down by actual experiments from, ages ago.
Okay.
And it just completely fails to explain so much of what we know gravity does, things that general relativity explains perfectly.
Things that point directly to gravity being about the geometry of space-time.
Exactly.
Okay, so let's start with general relativity then. That phrase you always hear. Matter tells space-time how to curve, and curved space-time tells matter how to move. It sounds neat, but how did Einstein even get there? From Newton's force to this?
Well, a really key starting point was something called the principle of equivalence. It's a thought experiment, mostly.
Okay, lay it on me.
Imagine you're in a sealed room, no windows. If it's just sitting on Earth, you feel your weight right. Drop something, it falls. Standard stuff.
Yep.
Now, picture that same room out in deep space, far from any gravity. But it's inside a rocket that's accelerating upwards, exactly matching Earth's gravity, 9.8 meters per second squared.
Ah, so you'd feel pushed down onto the floor.
Exactly. You'd feel that pressure. And if you drop that ball again, from your perspective inside the room, it would fall to the floor, just like on Earth.
Huh.
And the crucial point Einstein made is there's no experiment you could do inside that room locally that could tell you whether you're sitting still on Earth or accelerating in space.
Wow. So gravity feels like acceleration, and acceleration feels like gravity. Locally, they're indistinguishable.
Precisely. And that's a profound insight. It suggests gravity isn't a true force in the same way electromagnetism is. You can't just switch frames of reference and make an electric field disappear.
No, I guess not.
But gravity, you can effectively switch it off locally. Think about astronauts in orbit or someone in a free-falling elevator before it hits the bottom. They feel weightless.
Because they're falling with gravity.
Exactly. They're following their natural path in that gravitational field. It suggests objects aren't being pulled by a force. They're just following the straightest possible path through a background that's itself distorted or curved.
Okay, that's a big shift. So it's the path through space-time.
Right. Think about this. Drop two ball bearings side by side from way up high. They're both falling freely towards Earth's center.
Okay.
But because they're both heading towards the center, their paths aren't perfectly parallel. They'll actually get slightly closer together as they fall. They accelerate relative to each other.
Ah, like lines of longitude meeting at the pole.
That's a great analogy. That effect, we call it a tidal effect, tells you space-time isn't uniformly flat. It's like a quilt made of tiny flat patches, but each patch is tilted slightly relative to the ones next to it.
So you need curved geometry to describe the whole thing.
You got it. Just like you need geometry to describe the surface of the Earth, even though locally it looks flat.
So if space-time is curved, what's actually doing the curving? Is it just mass, like the classic bowling ball on a rubber sheet analogy?
That analogy is, well, it's helpful for visualizing space bending, but it's also kind of misleading.
How so?
Two big reasons. First, it completely misses that gravity also warps time, not just space. Second, objects don't just roll down the slope on the sheet. In GR, they're following the straightest possible path through that warped spacetime.
Okay, so it's not just mass.
No. Einstein's field equations tell us that the curvature is related to the presence of all forms of energy and momentum, and even pressure. Mass is just one form of energy, thanks to EMCR.
Right.
So it's the total mass-energy content that dictates the geometry. And it's a dynamic relationship. The mass-energy curves spacetime. And that curved spacetime tells mass-energy how to move. It's a two-way street.
You mentioned time warping. That's always sounded like science fiction. How does gravity actually affect time?
It's definitely one of the weirdest but best confirmed parts of GR Carry. Gravity literally makes time pass more slowly.
Slower. Like my watch would tick slower if I was near a black hole.
Absolutely. The stronger the gravitational field, the closer you are to a massive object, the slower time flows relative to someone further away. It's not an illusion, it's a real physical difference. We call it gravitational time dilation.
Wow.
And actually, for things moving at everyday speeds, like planets orbiting the sun, the most important part of the space-time curvature is often the warping in the time dimension.
Really? How does that work?
Think about just sitting here on Earth. You're actually moving through time pretty fast, right? The Earth's mass warps space-time, specifically causing time to flow slightly slower down here than, say, up where GPS satellites orbit.
Okay.
Now, an object in freefall, like that ball we dropped earlier, is essentially trying to follow the path through space-time, where its own internal clock ticks the fastest, maximizing its proper time, we call it, in this warped time dimension near Earth. The straightest path, the one that maximizes its time passage, involves trading some of that rapid movement through time for movement through space.
And that trade-off, that's what we see as falling.
That's exactly what we perceive as the acceleration of gravity, yes. It's objects trying to follow the laziest path through warp time. And a simple mechanical drag model. It has absolutely no way to explain this warping of time itself.
So objects aren't really being pulled down, they're just following the path of least resistance through warp time.
In a manner of speaking, yes. More precisely, in general relativity, a freely moving object follows what's called a geodesic.
A geodesic.
Think of it as the straightest possible line you can draw through a curved space, or curved spacetime. Like a great circle route on Earth is the straightest path between 2 points on a sphere.
Got it.
So a planet orbiting a star isn't being constantly yanked off course by some invisible force. It's simply following its geodesic, its straightest path, through the spacetime that's been curved by the star's mass.
And that solves Newton's problem. The action at a distance thing?
Exactly. There's no spooky force reaching across space. The Earth only feels and responds to the shape, the geometry of space-time right where it is. It's all local.
Okay, that paints a pretty compelling picture for general relativity. Elegant, even. But let's pivot now to this other idea, the drag effect. It sounds intuitive, maybe simpler. Is it a totally new concept, or does it have history?
Oh, it definitely has history. It's not new at all. These kinds of drag or shadowing ideas are conceptually very similar to theories that were looked at and, frankly, disproven centuries ago.
Like what?
Well, you had things like Lesage's theory back in the 18th century. He imagined tiny particles, ultramundane corpuscles flying everywhere, pushing objects together because objects would shield each other, creating a net inward
A
force.
shadow effect, right.
Exactly. Or later in the 19th century, when people believed in the luminiferous ether, the stuff light supposedly traveled through there, were ether drag theories. George Stokes, for instance, suggested maybe planets drag the ether along with them completely.
So these are kind of the ancestors of the modern drag idea we're discussing.
Direct conceptual ancestors, yes.
And for physicists today, what's the immediate, biggest red flag when they hear gravity as drag?
Energy. It always comes down to energy dissipation. Friction, drag, Any mechanism like that must take kinetic energy, the energy of motion, and turn it into heat. That's basic thermodynamics.
Okay, so if gravity was drag,
A planet orbiting a star would constantly be losing energy. It'd be like it's moving through molasses, very thin molasses maybe, but still losing energy.
which means
It would inevitably slow down, and if it slows down, its orbit can't stay stable. It has to spiral inwards, closer and closer to the star.
So if that was true, Earth shouldn't be here. It should have spiraled into the sun ages ago.
Absolutely. The fact that our solar system is stable, that Earth has been orbiting for, 4.5 billion years, that's probably the single most powerful piece of evidence against any simple drag model.
And where would all that lost energy go? You said heat.
Yes, heat. And it's not a small amount. Maxwell actually calculated this back in the 19th century for a Lesage-type model. He figured out the heating effect on Earth would be, catastrophic.
How bad?
Enough to raise Earth's temperature by trillions of degrees per second. It would vaporize instantly.
Trillions. Okay, yeah, that's decisive.
The simple fact that planets exist, that they aren't boiling infernos, tells us gravity isn't frictional.
So beyond just the theory and the energy problem, were there actual experiments back then that tested these ideas, these drag theories?
Oh yes,
Yeah.
definitely. A really crucial one involves something called stellar aberration.
Aberration.
Yeah, it was discovered way back in 1728 by James Bradley. It's this tiny shift you see in the apparent position of stars over the year, caused by the Earth's velocity as it orbits the sun.
How does that work?
Think about running in the rain when the rain is falling straight down. You have to tilt your umbrella forward a bit, right? Because you're moving into the raindrops.
Okay, yeah, makes sense.
Same idea with starlight. Because the Earth is moving, a telescope has to be tilted slightly forward in the direction of Earth's motion to catch the light coming straight from a star.
And how did that disprove ether drag?
Well, if the Earth dragged the ether along with it perfectly, as Stokes suggested,
Then relative to the telescope, the ether wouldn't be moving.
exactly, it'd be like standing still in the rain. The light would just come straight down the tube, no tilt needed.
But we do see the tilt. We observe aberration.
We do. And it matches exactly what you'd expect for an Earth moving through a non-drag medium, or just through space itself. So that observation directly killed the idea of complete ether drag.
Huh. What about Michelson-Morley? Didn't that try to detect the ether?
It did, yeah. It was designed to measure Earth's motion through a stationary ether. Famously, it found nothing. But even that null result caused big problems for partial drag theories, too. It created paradoxes that were only really sorted out when Einstein came along with special relativity and basically said, we don't need the ether at all.
Right. Just get rid of it. Okay, so the drag idea also seems to suggest that the shape of a planet, the fact that it's spherical, is somehow the cause of this drag. How does that line up with how we think planets actually form?
It gets the cause and effect completely backwards. A planet isn't spherical, and therefore it causes gravity drag. It's the other way around.
Gravity makes it spherical.
Exactly. The spherical shape of large bodies, planets, stars, is a direct result of gravity itself. Gravity pulls inward, uniformly in all directions. Once you get enough mass together,
Like above a certain size.
right, above a certain mass threshold, that inward pull of self-gravity becomes stronger than the material's own structural strength, its rigidity. And it just forces the material into the most compact, lowest energy shape possible.
Which is a sphere.
Which is a sphere, or very nearly a sphere,
Yeah.
allowing for rotation.
So that's why asteroids and small moons are all lumpy and irregular. They're just not massive enough.
Precisely. Their own gravity isn't strong enough to overcome their material strength and pull them into a round shape. So the causal chain is clear. Gravity causes stuff to clump together, accretion, and enough mass under gravity naturally leads to a spherical shape.
But the drag model flips that. It says the sphere causes the gravity effect.
Yeah, which leads to a kind of chicken and egg problem, doesn't it?
Yeah.
If the sphere causes the drag gravity, what force made the initially spread out non-spherical cloud of gas and dust collapse into that sphere in the first place?
Yeah, it can't explain its own starting point.
It completely fails to explain the formation of the very objects it needs as its mechanism.
And what about the thicker matter idea? That as you get closer, you're moving through denser stuff.
That seems to confuse the physical density of the planet's material, the rock iron deep inside, with the nature of its gravitational field.
Okay.
Gravity, as we understand it through GR, is a field interaction. It's not like you're physically plowing through the planet's substance when you orbit it. You're in the vacuum of space.
You're interacting with the field, not the stuff itself.
Right. Or more accurately, you're responding to the curvature of space-time caused by the total mass energy of the planet. which extends outwards. A satellite orbiting Earth isn't hitting more stuff than one further out. It's just in a region where spacetime is more strongly curved because it's closer to the source of that curvature. There's no thicker medium, just a stronger field or deeper curve.
Okay, that makes sense. So that really brings us to the positive evidence for spacetime curvature. What are the big knockout empirical proofs that show gravity really is geometry, not drag?
Well, one of Einstein's earliest and most spectacular predictions was about light. If gravity is spacetime curvature, then even massless things like photons of light should have their paths bent when they pass near a massive object.
Because they have to follow the curve of spacetime?
Exactly. They follow their geodesic, the straightest path through that curved region.
And this was the famous Eddington eclipse experiment in 1919.
That's the one. Arthur Eddington led expeditions during a total solar eclipse. They took photos of the stars right near the edge of the blacked-out sun.
And compared them to photos when the sun wasn't there.
Right. And they found the stars' apparent positions had shifted. They looked further away from the sun's edge than they should have. And the amount of that shift, that deflection, it matched Einstein's prediction perfectly, not the older Newtonian prediction, which was half as much.
Wow, that must have been huge news.
It was GR's first major public confirmation. And today, we see this effect, gravitational lensing, all the time. Massive galaxy clusters act like giant cosmic telescopes.
Bending light from things behind them.
Exactly. Bending and magnifying light from incredibly distant galaxies, letting us see further back in time than we otherwise could. It even helps us map out dark matter, which we can't see directly, by how it lenses light.
And a drag model just can't explain that.
Not even remotely. Light is massless. Photons have no physical substance to drag against or interact with via friction. The fact that light bends is direct, undeniable proof that gravity affects the actual fabric of spacetime itself. The light is just taking the straightest available path.
Okay, light bending is a big one. What about time? You mentioned gravitational time dilation. How well tested is that?
Extremely well tested. It's maybe the most mind-bending prediction, but the evidence is rock solid. Time genuinely runs slower in stronger gravity.
How did they first test it?
A classic early test was a Hatfield-Keating experiment in 1971. They flew incredibly precise atomic clocks on commercial jets eastward and westward around the world.
And compared them to clocks that stayed on the ground.
Yep. And when the traveling clocks returned, they were slightly out of sync with the ground clocks by just nanoseconds, billionths of a second. But the difference perfectly matched the combined predictions of special relativity, due to speed, and general relativity, due to altitude and thus weaker gravity.
Nanoseconds. That's amazing precision.
And it gets better. More recently, physicists using hypersensitive optical atomic clocks have measured the time difference over a height difference of just 1 meter in a lab.
1 meter? Seriously?
Time runs measurably slower, closer to the floor than higher up, just due to Earth's gravity.
So, my GPS, in my car or phone, that relies on this.
Absolutely, 100%. It's a constant real-world application of relativity. The GPS satellites are orbiting way up high, where Earth's gravity is weaker.
So their clocks run faster.
Exactly. Their onboard atomic clocks tick slightly faster than identical clocks down here on the surface.
Yeah.
It's about 45 microseconds per day faster just from the gravity difference. Then you factor in their speed, which slows time down a bit via special relativity.
Okay.
The net effect is the satellite clocks gain about 38 microseconds, 38 millionths of a second, every single day compared to ground clocks.
And if the GPS system didn't account for that tiny difference,
your position calculation would drift off by about 10 kilometers or 6 miles every single day. The whole system would be useless within hours.
Wow. So my phone navigating me is basically running a continuous global experiment confirming Einstein was right about spacetime.
That's a perfect way to put it. The daily function of GPS requires accounting for the reality of spacetime curvature and time dilation, a drag model. It offers zero explanation for why time itself should care how close it is to a planet.
Okay, that's incredibly compelling. Light bending, time warping. What else? Was there a final piece?
The final spectacular confirmation. Gravitational waves.
Ripples in spacetime.
Exactly. If spacetime is a real physical fabric, then accelerating massive objects, especially really violent events like two black holes colliding, should create disturbances, ripples, in that fabric.
Like throwing a rock in a pond.
Sort of, yeah. And these ripples should travel outwards at the speed of light, carrying energy away from the event.
And we detected those. How?
Well, the first strong indirect evidence came back in the 70s. Hulse and Taylor discovered a binary pulsar system, two neutron stars orbiting each other. By timing the pulses incredibly accurately, they could measure the orbit. And they found the stars were slowly spiraling inwards, getting closer together. They were losing orbital energy.
At exactly the rate GR predicted they should be losing it by emitting gravitational waves.
Precisely. It was a stunning confirmation, and they won the Nobel Prize for it.
But that was indirect. We couldn't see the waves themselves then.
Correct. The direct detection was a landmark moment in physics, relatively recently, September 14th, 2015.
LIGO?
LIGO, yes. The Laser Interferometer Gravitational Wave Observatory. Two giant detectors, one in Louisiana, one in Washington State. They detected this incredibly faint signal, a chirp, from two black holes merging over 1 billion light years away. It was the signal of spacetime itself being stretched and squeezed as the wave passed through Earth.
Actually measuring the distortion of space.
Measuring the distortion of space, yeah. Since then, LIGO and its partner Virgo in Europe have detected dozens more events merging black holes, merging neutron stars. It's opened up a whole new way to observe the universe, gravitational wave astronomy. We can literally hear the cosmos now.
And again, a drag model has nothing to say about this.
Absolutely nothing. There's no mechanism in a simple drag or friction model for creating waves in space-time that propagate at light speed. It just doesn't compute.
Okay, so with all this evidence, light bending, time dilation, GPS, gravitational waves, it seems like general relativity is on incredibly solid ground. Is it basically the final word then? End of story?
Well, not quite. As successful as GR is, physicists know it's not the complete story. There are definitely areas where it's incomplete or where we suspect it might need modification.
Like here.
The two biggest areas are quantum gravity and cosmology.
Okay, quantum gravity, unifying GR with quantum mechanics.
Right. That's probably the single biggest challenge in fundamental physics. GR describes gravity and the large-scale structure of the universe beautifully. Quantum mechanics describes the other forces and the behavior of matter at the smallest scales.
And they don't play nice together.
They fundamentally clash in extreme situations, like at the singularity inside a black hole or at the very moment of the Big Bang. Our theories break down there. We need a theory of quantum gravity to understand those regimes, and GR by itself, isn't it?
Okay, so that's one area. What about cosmology?
When we apply GR to the universe as a whole, the equations match what we observe, things like the expansion of the universe, the cosmic microwave background, only if we assume the existence of two mysterious ingredients, dark matter and dark energy.
Right. Stuff we can't see directly.
Exactly. We see the gravitational effects galaxies spinning faster than they should based on visible matter, suggesting extra gravity from dark matter. And the expansion of the universe is accelerating, which seems to require some kind of dark energy with repulsive gravitational properties pushing things apart.
But we haven't found these things in a lab yet.
No. And because we haven't detected them directly, some physicists wonder, could it be that dark matter and dark energy aren't new substances after all? Could it be that our theory of gravity, general relativity, needs to be modified on cosmic scales?
Ah, so maybe GR itself is slightly wrong at very large distances or low accelerations.
That's the question some people are asking. It's an active area of research.
So there are actual legitimate alternative theories to GR being worked on.
Oh, absolutely. But, and this is a crucial distinction, they're profoundly different from the simple drag effect model we've been discussing.
How so?
Any serious modern alternative to GR must, as a starting point, reproduce all the successes of GR, where it's been tested to incredible precision, like in our solar system, with binary pulsars, with GPS.
So they can't just throw out space-time geometry.
No way. They typically work by modifying or extending GR's framework.
Right.
They might add new fields, change the mathematical structure slightly, perhaps introduce new interactions.
To try and explain things like galaxy rotation without dark matter or the cosmic acceleration.
Exactly. They're trying to address specific observational puzzles or theoretical problems like quantum gravity, while still respecting the mountains of evidence that support GR in its tested domain. Examples might include things like MOND, modified Newtonian dynamics, or various FR gravity theories, or string theory approaches.
So these are highly complex mathematical theories, not simple mechanical analogies.
Very much so. They have to be mathematically consistent, make testable predictions, and fit all the existing data, not just cherry-pick certain phenomena. It's a very high bar.
Okay. So wrapping things up then, we've taken quite a journey today, really contrasting this established, tested picture of gravity as curved spacetime with that more intuitive, but as we've seen, deeply flawed idea of a drag effect.
Yeah, and looking at the big picture, that drag model just fundamentally breaks down. It can't explain why orbits are stable for billions of years. It predicts they should decay rapidly and generate impossible amounts of heat.
Right, fatal flaws from the start.
And then, critically, it has absolutely no explanation for things we know happen. The bending of light, which has no mass to drag, the slowing of time itself near massive objects, the existence and properties of gravitational waves. GR explains all of these naturally.
And things like GPS rely on that explanation being correct every second of every day. It really drives home that space-time curvature isn't just some abstract math.
No, it's a physical reality. It's
Yeah.
woven into the fabric of the cosmos, confirmed by everything from, yeah, your phone's navigation, all the way up to the echoes of merging black holes billions of light years away. It's real.
Which leaves us with a pretty profound thought, doesn't it? If gravity isn't a force pulling things, and it's definitely not some kind of cosmic friction or drag,
Yeah.
what does the fact that it's geometry tell us about reality itself?
That's the big question, isn't it? If one fundamental interaction turns out to be about the shape of the universe's fabric, what else might be? Are other forces, other particles, perhaps also manifestations of some deeper hidden geometry we haven't fully grasped yet?
What fundamental truths are hiding in the fact that space-time can curve? It definitely makes you wonder. We really encourage you listening to dig into these ideas more. Keep asking those big questions.
Absolutely. There's always more to explore, always more to learn to this amazing universe.
Well, thank you for joining us on this deep dive into the heart of gravity. We hope you're leaving feeling a bit more informed, maybe a little less dragged down by old ideas, and hopefully a lot more curious about the incredible fabric of reality.